Okay, the next thing we're going to talk about here is the effects of altitude and barometric pressure on trajectory of a bullet. And let's start off again. We've been kind of going through the 23-10 just to see what it has to say. And let's see how they describe this. Altitude, barometric pressure. Kind of in the same category here. Since the air pressure is less at higher altitudes, the air is less dense. Thus, the bullet is more efficient and impacts higher due to less drag. Yep, they pretty much got it there. And what's going on here is barometric pressure is basically caused by the force of gravity pulling down on the air. And when you get a whole bunch of air basically piled on top of itself, the stuff at the bottom of the pile is going to have more pressure than the stuff at the top of the pile. It's just like you can amplify the effect in water. The deeper you go in water, the more weight you have above you from all the water on top of you, so it's going to be way higher pressure, right? So it's a pretty simple concept, actually, right? So at low altitudes, like at sea level, you're going to have higher pressure than you are at high altitudes, like 10,000 feet up in the mountains or something. So at lower altitudes, your impact is going to be quite a bit lower. You're going to have to come up in elevation more, as the drag on your bullet was significantly increased due to the higher density at lower altitude. If you go up high in the mountains, the air is a lot more thin in the mountains, obviously, so thinner air equals less resistance on the bullet as it flies, and your impact is going to be higher because your velocity is going to stay faster. So the horizontal portion of your velocity is not going to decrease near as fast as it would in thicker air, right? Okay. So how do long-range shooters deal with this problem of changing barometric pressure? How do they do that? Well, there's several different approaches to this. And one common thing that you might hear is a lot of shooters talking about how you got to really watch your altitude. And they'll have a lot of tables set up showing the change of impact of their bullet at different altitudes. A lot of other people will talk about the effects of just straight barometric pressure. So what's the deal? You got to account for both altitude and barometric pressure. How does this work? Well, really, the two are kind of in the same category. And what I mean by that is altitude is really only a significant factor because your barometric pressure changes with altitude. So you're going to have standard pressures at different altitudes. Now, when I say standard pressures, that means a typical average pressure at a given altitude. Obviously, the things going on in the atmosphere, here in the troposphere that we live in, it's the lower layer of the atmosphere, is a lot of weather. And there's lots of different kinds of movement to the air masses, and you have pressure fronts moving around. So your barometric pressure will fluctuate with altitude. And it will fluctuate quite a bit. So it is definitely something we're going to have to correct for, and I'll show you some examples of how much it'll change your point of impact in just a minute here. But first, we need to kind of understand what we're looking at. At sea level, your standard barometric pressure at sea level is going to be approximately 29.92 inches of mercury. Now, what's inches of mercury? There's different ways to measure barometric pressure. This is kind of the classic way to measure it and the way that I'm just going to reference. If you're more used to pascals or millibars, you can go ahead and set up all your ballistics tables to use those units of measurement. It doesn't really matter, but just for the sake of this video, I'm going to be using inches of mercury because that's probably the most used measure of barometric pressure in long-range shooting circles in America anyways. So what are inches of mercury? What's that mean? Well, basically the way a barometer works is you just like have a cup full of liquid mercury, Hg. When you see that, inches Hg, that's the designation for mercury. If you look on the periodic table, mercury is designated Hg on the periodic table. So that's what that means. A lot of guys kind of get confused. What's that? So what you do is you have a cup full of liquid mercury back in the old days, and then you put like a tube in that cup upside down so that the mercury can squish up in that tube. And what basically happens is as your air pressure increases, more of that mercury gets forced up into that tube. And the more pressure you have, the more air pressure you have, the more that mercury is going to kind of go up into that little tube there. So, and they had a particular way they'd build these things, but that's what they're talking about, is a physical measurement of inches of mercury moving up the tube. So on a barometer back in the day, the old school ones, you would have 29.9 inches of mercury squish up into that tube on a barometer. That's what that means, okay? So it's just a system of measurement. And nowadays it's all electronic, but they still have it, calibrated for that same measurement nonetheless. But if you look at the lovely picture of this standard pressures at altitude here with the mountain, you'll see that down at sea level, your standard barometric pressure, what you're typically going to see is approximately 29.92 inches of mercury. And if you go all the way up to 9,000 feet, it's 20.6 inches of mercury. Now, I kind of drew this kind of stupid. I should have put those red measurements of barometric pressure on the lines. But the 29.9 is for sea level, the 28.9 is for 1,000 feet, and so on. So basically the trend is the higher you go, the less the pressure you have. And you'll see that the difference from sea level to 5,000 feet is about 5 inches of mercury. So it's approximately, in the ballpark of 1 inch of mercury per 1,000 feet. But it's not linear exactly. The further you go up in the troposphere, the more quickly your barometric pressure lightens up. So at lower altitudes, it's less quick of a change. But as you get higher, if you were to graph it out, it's not a linear change. It does more follow kind of a J curve, kind of going up. But at the altitudes that we're talking about here, that you can breathe in and that you can actually physically stand on a piece of ground. Highest mountain in the world is only 29,028 feet or whatever. So you're not going to have to worry about those pressures, obviously. You're probably not going to really be shooting at anything over 10,000 feet in altitude unless you're on the Himalayan plateau or some really high areas, up in the mountains of Afghanistan or the Karakorums or something like that. But for our purposes, this graph is representative of the standard pressures at these different altitudes. And depending on what literature you're looking at or what kind of formulas you're using, these numbers will vary slightly because there's, different people have different numbers they come up with. But they're going to be about in that ballpark. So the way that most shooters have done this historically to account for changes in barometric pressure is most shooters did not used to carry a barometer in the field. They would get meteorological reports telling them, during the briefing or whatever, exactly what kind of conditions they'd be probably experiencing. So they'd plan for that ahead of time. But as far as carrying a barometer, most of them probably don't carry barometers, but they do carry charts that tell them approximations of standard pressures at different altitudes. And then when they're operating, let's say at 6,000 feet, they can know that most likely their pressure is going to be somewhere in the ballpark of 24 inches of mercury. And then they can adjust accordingly, according to their tables. And we'll show you how to get those tables set up here pretty soon after we're done with our ballistics. This is more the conceptual part, just teaching the concepts of what's going on. And we'll show an example in this video, but we're going to do a real detailed rundown of exactly how to set up all your ballistics tables for your particular cartridge and your load in your particular rifle. So I'll show you how to get set up with that before too long here, but first we got to cover all the basics and know what we're looking at. So here's the standard pressures at altitude, and that's the basic way that most shooters have done this. Now let's take a look here before we move on, what it would look like in the real world if we were to take a shot without correcting for changes in barometric pressure. Okay, so this first one, and we're going to be using the same ballistic tables that we were using on the last couple videos with the 308 Winchester 168 grain boat tail hollow point at 2,600 feet a second. Okay, and this is assuming the rifle is zeroed for a barometric pressure of 29.56. That's what we're going to designate as our so-called standard conditions for this little test. So here we go. We're shooting at this big old muley buck standing here at 1,000 meters. Okay, so that's what it would look like in your scope. And let's say we have a barometric change of just 1 inch of mercury. So as you're driving to go to your favorite hunting spot, you forgot about the slight altitude change, and you're walking around all day, and then you see this deer, and you figure, man, I'm just going to take the shot because I don't have time to correct for little things like barometric pressure. It should be pretty close. So if you did not correct for barometric pressure, everything else being equal, is ballistically talking about all our other factors being properly adjusted for your ammo temperature, ambient air temperature, other internal ballistic muzzle velocity changes and things like that. But if everything else was good and you forgot to just account for your barometric pressure change, here's where we would hit. Okay, over the top by enough to miss significantly, right? Looks like about 18 inches over the top. And that, again, it's a little bit to the right. That's because of at that range, you're going to have about 11 inches of spin drift added to your tiny amount of Coriolis effect at that range to the right. So that's not wind. That's just the other traverse factors coming into play there. So, oh, man, that was a miss, and it ran away. The buck was standing there, but you're not going to really have a lot of success hitting that buck running around at 1,000 meters. That was your one chance. He got spooked by the bullet, and you missed him. So a guy really should have corrected for that 1 inch of mercury change, just a tiny bit. Okay, let's take a look. Let's say you're going to go on a big trip. You're in the lowlands, wherever you live, and you zero your weapon at 29.56 inches of mercury, like we said before, and then you're going to get on the airplane, and you're going to go on a big hunting trip up in the mountains, Montana or Wyoming or someplace. And now you're at about 6,000 feet elevation. And you got your long-range rifle set up, and you got all your charts, and you confirmed them at your altitude, at your barometric pressure, okay? So let's say you see the same situation, 1,000 meters, a big old muley buck trophy is standing there, and you take a shot without correcting for it. Now, this is a 5 inches of mercury change. This is about 5,000 feet altitude difference, okay? How far are you going to be thrown off then? Whoa. They're going to make fun of you for missing by that much, okay? That's like way over the top. That's over 2 mils over the top. And at that range, that's a significant miss. You weren't even close. So you really should have corrected for that kind of barometric pressure change. So minor changes in altitude do affect the barometric pressure enough to miss by significant amounts. So unlike humidity, like we reviewed before, humidity hardly changed the point of impact at all. And you could pretty much ignore humidity on everything inside 1,000 meters without any kind of ill effects. But things like ambient air temperature and especially muzzle velocity changes due to ammo temperature, you saw were very significant. This is a very significant change as well. So barometric pressure is definitely something you want to keep an eye on. And the best way to do this, the way I'm going to show you guys how to get set up, is we're going to actually, rather than going off of altitude, we're going to measure our barometric pressure in the field. And the reason for that is there's a lot of other things that can affect barometric pressure besides altitude. Sure enough that, you're going to have standard pressures at these altitudes, but there's a lot of stuff going on. I mean, you can have, if you got inclement weather moving in, you're going to have pressure changes. Your pressure could drop. Usually not enough to throw you by a lot, but all these things added together can throw you. Or if you're in a real nice day where it's nice and sunny, you might have a high pressure zone. You could be approaching a low pressure trough. You could be even just in the deepening of a low-pressure trough in your area. This is all weather stuff we're talking about. You could have a reduction of the mass caused by the upper-level divergence, like vorticity or jet stream changes, and that'll change the surface pressure. You could have, like, moist air. We talked about how moist air is less dense than dry air, so you could have moisture advection, which would change barometric pressure. You could have warm air. We talked about how warm air is less dense than cold air. So you could have warm air advection. You could have rising air. There's a whole pile of factors that could, like a front moving in. You could have all these things that would significantly affect your barometric pressure in your local area. So a lot of times you'll be at altitude, you'll look at your chart, and it'll tell you, okay, here's what the pressure should be, and then you actually measure the pressure, and you're like, whoa, that's not what it said, right? So, and it will throw you off enough to miss. So that's definitely something you're going to want to actually measure in the field. And that's why in a peripheral equipment selection video, I did kind of stress getting some kind of barometer set up. And this is going to be a critical piece of equipment. I would recommend having a backup of some kind. Most GPS units, like the higher end ones, like not most GPS units, but my GPS unit, my Garmin GPS Map 60, I think it is, that has a barometer built in. They do have wristwatches that are pretty fancy, and I forget which brand names they are. I almost bought one, but I got enough barometers, so I'm good. But they have wristwatches that actually have barometers in them. They're like for fancy hiking guys or whatever. One of you guys sent me a link to a camping website or something, and they have like a analog barometer that's real handy. It looks like a keychain barometer, and I actually think I'm going to pick up one of those. And this, like many of the other reasons we've been talking about, all these different things, they constantly change in the atmosphere because weather changes and, all these different factors, they'll add up to significant misses, and it's hard to keep track of all this stuff. So don't get too worried. I am going to show you the streamlined version of throwing all this stuff together in a really user-friendly ballistics tables setup. So even though this might make your head spin when you figure out all these different things, and we haven't even got into internal ballistics really in detail yet, but it'll be very easy to figure out once we get it all put together. So, and another thing with barometric pressure you might have is diurnal variation in pressure caused like twice a day by what's called atmospheric tides. Just like the moon pulls on the oceans, because the moon changes its orientation, every month. It circles the Earth, right? So the gravitational pull actually moves the water around. Well, the sun and the moon does the same thing with the atmosphere, and you have atmospheric tides. But with the Earth, it's actually spinning, and its orientation with the sun completely does its cycle every 24 hours, right? So you have diurnal cycles, and that can change your pressure. It's usually not by a lot, but it is measurable. And like I said before, when you have all these different factors, especially if they're building on themselves in the same direction, you can have a significant change. And also, there's things like topography can really change how all this is put together too. Particularly in my area where I'm at, I'm in the continental interior up here, and the standard, we're at about 2,000 feet, and the standard pressure up here should be about 28.67 inches of mercury. But usually when I go out, it's about an inch higher than that. It's usually around 30 inches of mercury. So the standard pressures and temperatures at these different altitudes are a good thing to know, just in case you do break or lose your equipment and you have no way of measuring your barometric pressure. You'll at least have a ballpark figure, and you usually get pretty close. But you do want to measure this stuff if you have the capability. And of course, the more detailed of a shot you want to make, a smaller target at a longer range, you really, really have to accurately measure this stuff. Another very important thing you're going to have to be aware of, a lot of you guys might be tempted to use these super phones we got nowadays that basically know everything, like on that, what was that old TV show, Quantum Leap, where the hologram guy had that little computer he carried around named Ziggy, and it knew everything. Well, unfortunately, the barometric pressure that your phone might report might be based on the local, weather channel or something like that. So if you're out in the field and you think that your cell phone is going to pass as a barometer, you got to understand how weather stations report barometric pressures. What most of your weather stations do, like if you watch on the news and they're reporting, the barometric pressure today is 29 point whatever inches of mercury or so many millibars or whatever, they're correcting for altitude. So they're not actually giving you the measured barometric pressure that it actually is at the area. They're correcting for altitude so that they can get a comparison between areas of different elevation for the purposes of forecasting weather. so that they can see a low pressure zone and a high pressure zone basically in the air masses. And they're not really talking about actual measured barometric pressure values. So that's why if you look at a map of the United States and all the different barometric pressures on the Weather Channel or something, you might notice that like on the coast where it's sea level, you're going to have like one barometric pressure, and then you climb up the mountains and it's still, it'll vary a little bit due to high and low pressure zones, but it's not going to be like what we saw in the picture before with the standard pressures at altitudes. That's all being corrected for sea level. And so that's something you want to be aware of. Don't go off of the Weather Channel or your superphone or weather reports or meteorological places like that. They're doing something completely different than we are. They're trying to find out pressure trends in air masses. They're not actually measuring barometric pressure for the purposes of determining air density like we are. So you do want to have an actual barometer for yourself in the field. And even if you do have the option of your superphone telling you the actual measured barometric pressure at the surface wherever you're at, I just wouldn't trust that, because if you hit the wrong button or look at the wrong number, you're going to miss by a lot. So you just want to measure it. You actually want to have the instrumentation yourself in the field. So that's something to be aware of. And I'm not going to go into the math of exactly how they do their altitude corrections. What you need to know is basically that that's not going to work for our purposes. So you do want to measure it yourself. So another thing to consider too, and we'll get into some of this a little more when we're actually setting up our ballistics tables, and I'm showing you how to calculate the corrections for these, is shooting through different pressure zones. Now, if you're operating in mountainous terrain and you have to take a really long-range shot at a really steep gradient, either uphill or downhill, doesn't matter, where your projectile is going to be going through different pressure zones, you're going to have to kind of average that out. But again, it's not going to be a linear calculation, because you got to consider the shape of your trajectory. So let's look at this picture here. So we have a guy sitting up on a mountain here, and he sees the big old monster buck down there standing nice and proud. Okay, and we're going to already have everything else figured out. We're going to have our actual horizontal range corrected for, which I'll show you on one of these next videos here. We're going to show you how to account for actual angle of fire shots. But let's say all that stuff is corrected for. But you got to consider when you're doing your barometric pressure calculations that now you're shooting through different pressure zones. So you're starting off at approximately, 24.9 or so inches of mercury, and you're shooting down in this case. So as the projectile approaches the target, it's going to be transcending this zone of higher pressure. And so that's going to affect the impact of your bullet differently than if you're just shooting at a given pressure zone, if you're just shooting horizontally. But this only applies to real steep angle shots, but it does affect it. And if you look at the shape of the trajectory, you're going to notice too that, like we said before, it's not linear. Your trajectory is going to have the max ordinate to it, and so you're going to have more of the effect at the 5,000 foot, the higher elevation. That's going to be more of a flat trajectory during that portion. Where you get towards the terminus, it's going to really turn down a lot more steep, and it's covering a lot less ground, and your velocity's changed a lot by then too. So you're going to have to weigh that properly. You're going to have to say, okay, which one of these pressure zones is going to have the most bearing on the flight characteristics of this bullet, considering the trajectory shape. So it's a little more complicated than you might think, but it is important to understand what's going on here, so that if you do make a miss, or if you are accounting for some of these things, you can know which side of the firing solution to error on when you're doing your calculations. So in this case, you'd probably want to put more weight on the 24.9 inches of mercury zone, because that's going to affect the flight path of your bullet more than the higher pressure zone below it, because the shape of the trajectory puts the flight of the bullet through that zone for a much longer time. So it's going to have more bearing on the trajectory in that zone there. And if we look at the U.S. Army 23-10 again, we'll look at Table 3-1. this kind of generally shows the point of impact changes at different ranges for these different altitudes given here. We got 2,500 feet, 5,000 feet, and 10,000 feet. And like we said before, the only reason those altitudes are significant is because the barometric pressure changes with them. So one thing to note here is if you are going to be actually measuring the barometric pressure, which is the better way to do this, in the field, you're going to actually measure the barometric pressure rather than going off of standard pressures at altitudes. Then you can basically disregard altitude for most purposes, okay? The air density is the thing we're looking for. So if you don't have a way of measuring barometric pressure, then your altitude will be significant. And I would recommend keeping a standard pressures at altitudes table in your data book or something that you do carry a field, just in case. But as you can see in this table here, they have the different corrections, and they're pretty close actually on this. And another thing to point out here too is although that these numbers may be different than what we have calculated in our table, that's because there's going to be different variations in the weapons and ammunition that are going to significantly affect these point of impact values. So the main thing to take away from this is that there's no one cure-all table that you can just download someplace or that you can borrow from someone, even if they're shooting the same exact ammunition in their similar rifle. There are going to be enough changes between the bore in your rifle and the bore in their rifle and all the other dynamics of what's going on in their system versus yours that are going to affect the internal ballistics enough to throw off your muzzle velocity. So it will be different, and that'll translate to big differences in point of impact at long range. So for deer hunting purposes at medium range or close range, like 100 yards, you're going to drop a deer. You can change ammo, and it's not going to change your point of impact that much. But at long range, it's going to make a huge difference. So the thing is, you can't just have one chart for one load. And you're going to have to develop a very specific set of data for your particular rifle and how it shoots your particular ammunition. So, for example, I got my 338 Lapua Magnum with the 300 grain Match Kings loaded a certain way. If someone else had a similar rifle, even with the same length barrel and same loads, and they needed a set of tables, it would be very difficult to give them a reliable set of data that they could actually use effectively, because the changes, particularly in internal ballistics, are going to add up to translate to a pretty good miss most of the time. And I'll show you later, like I said before, exactly how to account for all these things. That's why we have to go through all the pain of actually understanding all these different concepts, so that when we get to the part where we're going to be setting up our own ballistics tables for our particular weapon system, you'll actually know how that works, and we'll actually be able to get everything adjusted for precisely. And hopefully you'll be able to pull off all those shots that everyone would have considered impossible. So as we demonstrated a couple minutes ago, barometric pressure is definitely one of those things we're going to have to pay close attention to. We are going to be measuring our barometric pressure in the field and applying very precise corrections accordingly. Okay, so we're almost done with our basic external ballistics portion here. We just got to cover two more things. We're going to do a crash course on wind, and also we're going to do angle of fire corrections real quick. After that, we're going to get into our advanced ballistics. We're going to cover advanced internal, external, intermediate, and maybe a little bit of terminal ballistics. And then we should be able to apply all this knowledge and effectively construct ballistics tables that you can use to do really precise firing solutions for even extreme range. You'll be surprised how good they'll work if you do your part and pay attention to the details. Really, it's in the details. These things individually may be negligible, but they can add up to be like a ridiculous miss if you don't correct for them. Okay, so hopefully our next video doesn't blow too bad. We're just going to do a quick crash course on wind, and then we'll come back and revisit it in greater detail when we're actually putting it all together at the end.